All right, so here's another example where we're going to take a look at some switches. Now this one is actually the same one that I used in the path of least resistance video. So you can take a look at that. We're gonna go through this one relatively quickly, do some predictions on it, but also add a little bit of numerical stuff in here because many times you're asked about what's going to happen numerically. Now, one of the things that I will point out, while it's not always the case, but it is common on the AP exam, they'll give you arrays of resistors that all the resistances are the same or have a simple relationship. In this case, because of the equipment that I have, all of these light bulbs are going to be pretty much the same resistance, at least as much as we can in mass production. So we're going to say that they all have a resistance of R. Okay, so here's what we've got. I've got a switch that is currently open, so no charges can flow through that. And the whole circuit right now is actually off because I've broken the circuit here. So when I turn this on, we end up with the following. We've got, in fact, let me draw this out so that we can see it in our circuit diagram. We've got something like this. I've got a switch here. And then I've got two resistors over here. Great. And all of them have a resistance R. We could call this one A, we could call this one B, C, and D. Great. Now, common thing to ask is this. Which one is the brightest? Well, in our current configuration. Well, looking over this, we know that whatever our potential difference is, I'm going to stop draining my batteries for just a minute, we're going to have some current, I, that is coming out of the battery. Now, that current has to go through A. So A has, for its power, its brightness, I squared R. Okay? Now all that current continues going, and none of it can go through B because we've broken the link there. It's not closed, so none of these charges can move forward, so no charges can go down in there. So this is a common thing where I'll tie it again to what we've talked about before. Some people think, oh, well, some of the charges will go in there and then stop at the switch. No, there are already charges there because there are atoms there. If the switch isn't closed, then this one doesn't jump over, so this one can't, this one can't. Basically, that's a line that's already come to a stop. No charges are going to go down that path. All of them go this way. Okay, and then they go across C. C gets the entire current, so it also has the same power. It should have about the same brightness as A. And then it goes across D, which should, since it has the same current and the same resistance, it should have the same brightness as A. And then we have our current come back in over here. So we predict that with this switch open, all three of the light bulbs, because they're identical and because they're getting the total current from the circuit, they should be the same brightness. Oops. Helps if I do the right thing. And we see that, yes, lo and behold, they're all pretty much the same brightness. Now, in real life, in case you're going, that one looks a little dimmer than the other. Remember, A, you're picking it up on a camera, and B, not all of these light bulbs are exactly perfectly the same. They're pretty close, though. So we see our end result. Okay, now I've put this switch in here. So we've got a setup. They're all the same brightness, and we can predict that. Let's see what happens when I close this switch. And let's predict what happens. Okay, so there are a few things that I want you all to understand about this. First off, we're going to go through and we're going to use the comparisons that we've done before. This is the equivalent of me opening a door, another path. So we've got everyone trying to get out of the gym. I've opened a door. So what does that say about the total number of people getting out of the gym? Well, that means that our current is going to go up. And all of it goes through A, which means A will get brighter. A is going to get brighter. Great. But we're going to have some of it go down through B, some of the charges go down through B, and some of them go off through C and D. It turns out that now that even though our total current has increased, because we're splitting it, C and D should end up with less current going through it. So C and D are going to get dimmer. And then finally, B is obviously going to get brighter. I say obviously because it's off right now, and I'm actually going to get some power out to it by closing this loop and letting this line start moving, getting energy over to the resistor. So here we go. We expect that A is going to get brighter, C and D are going to get dimmer, and B is going to get brighter. And lo and behold, that's what we get. In fact, right now, with the light levels that you have, you may think that C and D have just gone completely out, but that's not true. In fact, I can prove it to you, because if that was not part of it, if I break this circuit, you'll see that these change. So they're there. I could have also unscrewed the bulb slightly so that it can't go through anymore. That being said, I've got these plugged in. We did see that A got brighter, B got brighter because it actually started getting power, and C and D got brighter. Now, the other thing that we can conclude is because all of them have the same resistance, this total branch here has a resistance of R, whereas this total branch has a resistance of 2R, which means we should end up with twice the current going through this branch than we should through the other. That's some of the fraction stuff that you can work a little bit with, and hopefully with your practice, you've been getting down a little bit more. Twice as easy to get through this, so twice as many people, charges, are going to get through it in a given time. We end up with twice the current. Over here, we have maybe about 0.4 amp, and then here, so that's going through this, and over here, we've got probably about 0.7 amp, so pretty close to twice. Part of that may be these meters aren't the best ever. All right. Great. So what happens if, now let's work through this some more. What happens if I were to break this one? That's closing one of the branches off. Well, we've already kind of seen it, but if I close a door, that's going to make it harder for people to get out of the gym, so we're going to have a lower total current. Our total current is going to go, let me use a different color, down, and all of it goes through A, so A is going to get dimmer. But even though we have a lower current overall, lower number of people getting out of the gym, now all of them have to go through B. B is probably going to get a little bit brighter. Even though we have less current overall, we end up with all of it going through B. So if I break this, we end up with these going like that. On top of that, we know that both of these have to come back down to now the same brightness. However, it will not be the same brightness as these. Main reason why is it's easier with only the 2 resistors. My current here is actually higher than if we had the 3 resistors and this one was broken. So since this is 3, we have less current than if we had this. These are only 2, so we have a little bit more current. You'll notice that this is a little bit brighter. Okay, I'm going to break this all together. So that's taking a look at that. There are a couple other things that I want to look at with this being a large circuit. We've got an idea of what's happening with the current, but let's see. Let's do some rough calculations here. Let's say that my battery is, I don't know, 10 volts. It's not, it's actually 3 volts, but let's just give it some numbers so that we can explore this a little bit. Okay, and let's say that each of our resistors are 10 ohms. Great. So at the beginning, when the switch is open, our total equivalent resistance for the circuit is 10 plus 10 plus 10 because they're all in series. So that'd be 30 ohm. We would have 10 volts divided by 30 ohms, so we would end up with something like a current of 0.333 amp, a third of an amp. Okay, that's not matching the actual numbers we have here because I don't know what the resistance of these light bulbs are right off the top of my head, and I don't feel like measuring them. And my batteries are actually 6 volts, not 10 volts, but this is good enough for what we want. Okay, so we have 0.33 going through this one, and through this one. They all have the same current. But what happens when I actually close this switch and we have all of this connected? Well, at that point, we've got this is 10 ohms and this is 20 ohms. So 1 over 10 ohms plus 1 over 20 ohms equals 1 over our equivalent resistance. My equivalent resistance there would be, what's that going to be? 20 divided by 3? Yeah, 20 divided by 3 ohms, which should be 0.067. Is that right? Let's see. 20 divided by 3. Oh, sorry. No, that's 6.67. I was moving it the wrong way. That's way too small. 6.67 ohm. And then that would be in series with A. So our total equivalent resistance with the switch closed is going to be 16.67 ohms, which is less than the 30 ohms that we used to have. I apologize. I should probably do this in a different color. So I close this switch, and we end up with an equivalent resistance of 16.67 ohms, which is less than the 30 ohms. As I said, we've opened a door, we've made it easier for the charges to get through. Okay, so now that we've got that, we could find that our total current should be 10 divided by 16.67. We end up with our total current becomes 0.5998, so we'll call that 600. 0.6 amp, which is 600 milliamp. Now, the current did not double, but it almost doubled. We got quite a bit more current, which is exactly what's happening when I do this. We end up with a lot more current. This ends up getting much brighter. By opening another door, it makes it much easier to get out of the gym. If, however, I close that door, then we end up back in a not necessarily great condition. Unless, of course, you want to keep people in the gym longer. Usually, I don't want to be there any longer than I have to. But let's then compare it to this, where I then said we were going to break this apart. We'll call this... I'm going to break that apart. And so now we only have two resistors, and the equivalent resistance on that, because they're both in series anyway, that's 10 plus 10, that's 20 ohms. Okay, so my current in that case would be 10 divided by 20 ohms, which is 0.50 amp, 500 milliamp. Now, that, I want to try and emphasize that so we can see it with numbers. I mentioned that when we had the 3 light bulbs, the resistance was higher, so our current would be lower. Now we've only got 2 light bulbs, and our current should be higher than that, but our current will be highest when we've got all the doors that we can open, and we get a little bit more out of it. Now that's also why we end up with these getting pretty dim, because they're only getting a small fraction of it. So if this is in fact 600 amp, or 600 milliamp, 600 amp is a frightening amount, then with this being twice as easy to get through as this, then you would have probably 400 milliamp going through here and 200 milliamp going through here. This one's twice as hard to get through, so it will have half the current. All right, so that's applying some of these ideas with what's going to happen with the switch. The final thing that I'll mention is this. Okay, so let's look at, we've looked at what's happening with the current, and we know there are different resistances. So here's what I'm going to do. I'm going to point out that initially, I'm going to break this so that I'm not wasting any of the stuff. We said that the initial current with the switch open was 0.333 amp. Okay, then we said that the current with the switch closed was 0.600 amp. And then finally, we said that the current with this branch broken, but the switch closed, would be 0.500 amp. Now, here's the other thing that I want you all to take into account. We know that the potential that all of these currents are going through resistor A. So delta VA at the very beginning is going to be equal to 3.33 volts. Delta V of A, for when we close the switch, all of the current, 600 milliamps, is going through there. We'd end up with 6 volts. It ends up with a lot more of the potential difference. And finally, when we break the other one, that would end up with 5 volts. I want to emphasize this because when you change one part of the circuit, you change pretty much everything. Honestly, the only thing that stays the same is going to be the resistance, because that's a physical value for each of the resistors. But the total resistance, the equivalent resistance of the circuit, will very likely change if you're changing parts of it. Now, the potentials are also going to change. All right, the final thing that I'm going to mention is this. Actually, no, we'll go ahead and stop there. We'll take a look at it in a different video. I think this is good for this one.